I think my video suddenly stopped, so let's again. I think I have shown that property number 1, property number 2. Yeah, just continue with what I have discussed. This is property number 2. We have shown the inner product of that set by itself is given as a norm of that, and then property number 3, that alpha x, the inner product of alpha x times plus beta y with z, that can be written as alpha x z plus beta y z. So that's what we're going to show. Alright, so if we split each of those elements, so what we have, because x with element x1, y1, z1, we have here at the beginning. Alright, x is x1, y, x2, and so on, y, y1, y2, and so on, and as well as z. So split those element by element. So what we have here, this given alpha x1 plus beta y1 z1 bar, that's bar because of from the definition of inner product, yeah, plus alpha x2 plus beta y2 z2 bar, and so on. We have alpha xn plus beta yn zn bar. Okay, from here you can easily recognize this as a, you can see here, this is just a normal multiplication because those elements. So x1 z1 bar, here we have x2 z2 bar, and so on. Then the other part you have y1 z1 bar, y2 z2 bar, and yn zn bar. So what we have, this is alpha, we have x1 z1 bar plus x2 z2 bar, and so on, plus xn zn bar, and plus the other part, beta is y1 z1 bar plus y2 z2 bar, and so on, plus yn zn bar. Okay, so that gives us, from there, that gives us alpha xz plus that one beta yz. So therefore, with this, satisfy these three conditions, so it means the given set is the Hilbert space. Now look at the symmetric kernel and the hilbert-schmidt theory. Yeah, we have seen the practically we have seen what is the symmetric kernel. So a metric we call it symmetric. The definition. A kernel we call it symmetric. A kernel k xt is said to be symmetric, is said to be symmetric, yeah, or also known as Hermitian. You can call it Hermitian, yeah, which means symmetric. If xt, this is equal to k xt, the conjugate of the kernel is equal to the kernel itself. So we have this is should be tx here, tx. Now we have xt, kxt, whereby that is the conjugate of that. So for the real case, yeah, for the real kernel, we have k xt, this is equal to k tx. This is for real. Yeah, but for the complex, we have this. Then we look at the operator. We call it as a freedom operator. Freedom operator. So we say the freedom operator K phi, this is K phi of X, and this is equal to A to B K X T phi T dt. So this K, we call it as a freedom operator generated by the kernel K. Now, if you have, let's say we have the freedom integral equation, Ux is equal to Fx plus, we have lambda integrate A to B Kxt ut dt. If you want to write in term of operator, or operator equation, you can write this by introducing this is the operator. So you can write this as a, here you can write as a Ux minus integrate A to B Kxt ut dt equal to Fx. Okay, in terms of operator, of course, here you can write as 1 minus lambda K U of T that equal to Fx. No, sorry, U of X. Okay, so this is in terms of operator. So instead of we write such a, it look quite long, whereas in terms of operator just a very short. Then we have adjoint operator. Adjoint operator. Yeah, adjoint operator. So we say the operator or adjoint, the operator adjoint or the conjugate to K given by K of some function phi, which is, phi is a function of X. This is A to B K Tx phi T dt. Yeah, that's very nice. So this we call it as a adjoint operator. So operator adjoint. So we have this relationship. If we do the inner product of k phi and phi, this is equal to phi k phi. So if satisfy that condition, then we say the operator is adjoint operator. Okay, adjoint operator. And then for the symmetric kernel, symmetric kernel, we know that symmetric kernel we have the relationship between the freedom operator and the adjoint operator. We can have K phi psi, this is equal to phi K phi. Yeah. So in this case, we call it as a self-adjoint. Self-adjoint operator. Also known as Hilbert-Schmidt operator. Yeah. Also known as Hilbert-Schmidt SCHMIDT, Hilbert-Schmidt operator. Okay, so thus in the integral operator K generated by a symmetric kernel is called as Hilbert-Schmidt operator. Yeah, Hilbert-Schmidt operator. Then we look at the Hilbert-Schmidt kernel. What is the Hilbert-Schmidt kernel? Hilbert-Schmidt kernel is the kernel K itself is called Hilbert-Schmidt kernel if it is Hermitian. You know what Hermitian is? Symmetric and square integrable. Square integrable. So the K kernel xt is called the Hilbert-Schmidt kernel. Hilbert-Schmidt kernel dt kernel if kxt equal to ktx, which is symmetric or Hermitian. And number 2, square integrable. Yeah? So satisfy this condition. AB kxt squared dx dt less than or finite. Now we look at the some of the frequently arise in many problem, the inequality. First, look at the source inequality. Yeah. Some inequality. So let's say source inequality. SCHWARZ inequality. Source inequality is given as so let fx gx in L2, yeah, means fx gx L2 function. It means that f is square integrable and g also square integrable. So that's L2 that I've defined at the beginning of our lecture. Then the following inequality known as the source inequality, which is the absolute of inner product of g, f and g. This is less than norm of f multiplied by norm of g. Okay, so we're going to prove this. We are going to prove two things. First thing, the inequality, the equality, yeah, where this equal to that, and as well as the inequality. So for the equality, if you take one of these 0, then obviously left equal to right. Yeah. So for equality, taking either f of g, in this case I take g equal to 0, then we have g equal to 0, then the result is obvious, left hand side equal to right hand side 0. So this is trivial. Okay, but if g is different than 0, for g different than 0, and for any scalar lambda, so we have f plus lambda g, f plus lambda g. Obviously this is positive, yeah, because this is the inner product of by itself. We have the norm of f plus lambda g, that's always positive. Or you can write, or you can split those things, so that gives us f f plus g, yeah, plus we have lambda g f plus lambda g. You know that this is positive. Okay, and then you split again. We have here is ff plus this gave you lambda by g fg, right, plus this one lambda gf, then this one you have lambda lambda by g. Okay, so that give us, yeah, this give you norm of f squared plus that one we have lambda conjugate, that you have f g, and that one you have lambda gf, that one you have lambda squared g squared. This is positive. And since g different than 0, then norm of g also different than 0. So if that the case, we can consider or we let lambda is equal to negative of fg over norm of g squared. Thus we have, yeah, just substitute that into that, so that give you f squared minus fg bar over g squared fg minus fg over g squared gf plus fg squared over g squared. This greater than 0, should be 4 here. Yeah, this is for lambda squared, and lambda is given by that, so we have 4. So you can cancel out this, that's with only left 2. Then you can write those as we have f squared minus fg squared over g squared, because this from fg conjugate times fg, so we have absolute of fg squared, yeah, minus here again we have fg bar over g squared plus fg squared over g squared. Okay, so I think one of this is that review that one of this is a positive. I think one of this is positive. Yeah, I think let me check. Conjugate, yeah. The conjugate part should be negative. Here should be negative here. Then here should be positive. Then we have positive there. So this cancel out. Right, so what left is f squared plus, sorry, minus, this one is minus f g squared over g, that's positive. So what we have from there is that f squared g squared minus fg squared, that one is positive, and hence from there it's easy to see that f g is greater than or equal to f g. Or you can write that the absolute of f g, inner product of f g, less than norm of f multiplied by a norm of g. Okay, and we also have next we have Minkowski inequality. Minkowski inequality, which is given as f plus g less than f plus g. So for the proof, I will put this as an exercise to you, and I want you to submit this by, I don't know, by next week. You have to prove. This is an exercise. Yeah, submit by, let's say before Monday next week. Before Monday next week. Okay, so I will put in the Putra Blast as an exercise there, so that you can submit through Putra Blast. Okay, and then last but not least, for today's lecture, I will give you the Bessel inequality. Bessel inequality. Yeah. So what is Bessel inequality? For fx, gx, L2 function, then this we call it as a Bessel inequality. Yeah, Bessel inequality. Ci squared I equal to 1 to infinity. We have f phi I squared, this is less than f squared, where f is real and continuous, and phi I of x for all I is an autonomous system. This is autonomous. Yeah, autonomous in L2, and Ci is Fourier coefficient of fx. Fourier coefficient of fx with respect to that system. The Fourier coefficient is defined as just a minute. Define the Fourier coefficient as Ci I as the inner product of f and phi I. The inner product of f and phi I, which is we have a to b fx phi I x dx. So with this, we call it as a Fourier transform of fx with respect to the system phi. Okay, so with this inequality, Bessel inequality, so we have three. Basically, I've explained, or I've shown you, or I've given you. We have source inequality, we have Minkowski inequality, Bessel inequality. For the Minkowski inequality, I want you to prove that, and I give you as I leave it to you as an exercise. For the Bessel inequality, the proof is given in the notes. I think I don't want to give it here. And also, the main part that we have discussed today is just I give you some definition on the Hilbert theory on integral equation. Yeah. So Freedom integral equation. We have Hilbert-Schmidt's theory of integral equation. So I think with that with that conclusion I stop this video. I stop here, and then we meet in other video. So bye bye for now.